Hi, I'm here today to talk about our paper DISTO, evaluating textual distractors for multiple choice reading comprehension questions using a new negative sampling technique. This is joint work with my former postdoc Bilal Ghanem, and I am Alana Fish. We're from the University of Alberta and the Alberta Machine Intelligence Institute. Multiple choice questions are great. They're a good way to quickly test comprehension because marking them is quick and easy. But each multiple choice question requires several distractors. Distractor answers are answers that are plausible but incorrect. Here's an example reading comprehension question. In this article, the last line is really the most important one. The giraffes from Brazil are waiting to look down on you. And the question here is, from the passage, we can guess that the animal giraffe must be very blank. The answer is tall. And the distractors in the data set are fat, long, and strong. So each one of those answers is a plausible option for the blank, but the best one is tall. So we need good distractors for good multiple choice questions. Good distractors are the way that you truly test student abilities. And that means that good distractors are hard to make, and they lead to additional cognitive load on educators. Is there a way to use language models to generate distractors? The answer is yes, and there's been several people working on generating distractors using large language models. But if we're going to use large language models in order to generate distractors, we need a good way to evaluate those distractors. We need to automatically evaluate them in order to test model performance amongst the many models that we might be training, as well as against previously released techniques. Typically, researchers have been using BlueScore in order to evaluate models, but BlueScore relies on the exact word overlap between a generated distractor and a gold distractor. Returning to our previous question, we can see the generated distractors are hairy, loud, and wide. Each one of these generated distractors is completely reasonable for this question, but none of them have any word overlap with fat, long, and strong. Therein lies the problem. Machine translation techniques rely on word overlap, but there doesn't have to be any word overlap between a gold distractor and a good generated distractor. That means machine translation techniques are probably not a good way to evaluate distractors. And that's because there's lots of plausible good distractors, and they can have many different words in them. So the question is, can we build a better evaluation method? Can we do better than the typical machine translation techniques that have been used so far? Well, first we need some data. Our plan is to train a new model that can produce scores for generated distractors. And in order to do that, in order to train that model to produce scores, we need examples of good distractors. Those are easy because we have them in our data set of multiple choice questions. But we also need examples of bad distractors, but they can't be too bad. We need medium bad distractors to show our model what a good distractor versus a bad distractor looks like. So we can generate bad distractors in a number of ways. One example of a bad distractor is an exact copy of the answer. An exact copy of the answer is not a good distractor because it can actually change the correct answer of the question, which is a problem. Another thing we could do is just randomly choose a distractor from any other question. But unfortunately, these are often too bad to be really good bad distractors. They're just too different from the current question. They're often completely off topic, and so they're easy to spot. So those are examples of bad distractors that are too bad. They're not good distractors. So how do we generate examples of bad distractors that are not so bad? A bad distractor has to be somewhat similar to a good distractor. So the way that we find distractors that are somewhat similar to our good distractor is using clustering. We can cluster embeddings for all of the good distractors in the full data set, and then for a given question, we find the cluster of that good distractor, and then select the distractor that is in the same cluster that is furthest from the good distractor. So in the picture here, the blue circle represents the cluster that the good distractor is in, and we would find the furthest distractor that's still inside the cluster, but is the furthest away from the good distractor. This gives us a distractor that is somewhat like the good distractor, but not too similar. Another way to create bad distractors is actually using an LLM. So we used an LLM, a new LLM, and its mask filling feature in order to rewrite a good distractor. So we start with a good distractor. Here the good distractor is they focus on Bible stories. And we use the masking feature of an LLM in order to replace the nouns, verbs, and adjectives. So they focus on Bible stories is a good distractor, and it would be rewritten as they drew on the sand by replacing each one of the nouns, verbs, and adjectives in the particular good distractor. So here we get a bad distractor that has some similarities to the good distractor. Great, now we have a data set with good distractors and bad distractors. And now we can train a new model to generalize those good and bad scores to new data. In order to do that, we will feed the question, answer, distractor, and article into a DISTO-Roberta model. We'll feed the first token from the encoder, the CLS token or classification token, through a sigmoid function and train that sigmoid to produce a 0 for a bad distractor or a 1 for a good distractor. This is the methodology that we ended up using for DISTO, but we actually tried several different things, and the details of that are in the paper. So now we have a model that can produce a score for whether or not a newly generated distractor is good or bad, which can substitute in as a metric for evaluating distractor generation models. So how does DISTO perform? So here are our results in a table, but I've blanked out the actual results to begin with because I want to talk about the columns and the rows. So to start with, we have machine translation techniques. Existing machine translation techniques are BLUE 1, 2, 3, and 4, as well as BLERT, which is a learned machine translation evaluation technique. Then we have B rank, which is the ranking of the models based on the BLERT score. Then we have the DISTO score, as well as the D rank, which is the ranking of the models based on the DISTO score. And here the rows are a bunch of different models. We selected models, pre-existing state-of-the-art models, as well as some of the ones we trained ourselves. I want to highlight here, though, that we are not interested in producing the best distractor generation technique here. Rather, we're interested in showing that there could be a better way to do distractor evaluation. So here are our results with the best numbers in each one of the columns bolded. You can see that the model that performs best by BLERT score also has fairly high blue scores, but it has the lowest DISTO score of any of the models we tested. Conversely, the model with the highest DISTO score has one of the lowest BLERT scores amongst the models we tested. So this shows that the relationship between BLERT scores and DISTO scores seems to be out of whack. To further highlight this point, here's a graph where the y-axis is the DISTO score and the x-axis is the BLERT score. You can see here that the DISTO and BLERT scores are actually negatively correlated, meaning that when the BLERT score is high, the DISTO score tends to be low and vice versa. Thus, it appears that the BLERT score, which is of course trained for machine translation, is probably not a good way to evaluate distractors. But in order to drive that message home, we did a human evaluation. Here we had Amazon Mechanical Turk workers say whether a given distractor from the dataset was either good or bad. And we can compare the average worker score to the labels from our gold data. So the gold data are 1 and 0 for good and bad, and the workers give good or bad score, and we average it over multiple workers. You can see that the gold data and the workers' scores are correlated 0.78. The gold data versus DISTO, 0.94, and workers versus DISTO, 0.81. So this shows us that the workers are similarly correlated to DISTO as they are to the gold data. And we also have quite high correlation between DISTO and the gold data because, of course, DISTO was trained on data from the same distribution as the gold data we used here. But of course, this gold data was from the test set. DISTO wasn't trained on these specific examples. So this shows us that DISTO is a good proxy for what people think are good or bad distractors. So to conclude, machine translation metrics are probably not a good way to do distractor evaluation. That's because there are lots of plausible good distractors, and they could have minimal word overlap with the gold distractors in a dataset. So we encourage people to include or consider something like DISTO instead when evaluating distractor generation methods. Again, this is joint work with my former postdoc Bilal Ghanem, who of course did most of the work that you saw here today. I am Alana Fish. If you have questions about this work, please contact me, Alana, at ualberta.ca. Thank you.